Okay. So I'm Ryan O'Donnell. I'm a second-year master's student in operations research and industrial engineering, and this will be the hopefully second video in this series for 371. Today we're going to talk about some basic concepts in R just to make sure everyone's on the same page, and then go through some relevant commands and discuss a little bit of the statistics that's going on in the third homework set. Most of this will also be relevant to the second homework set, so if you need to watch it for that, it would be useful as well. Okay, just talk about a couple of things. Some things have changed a little bit to make things a touch easier. So some of these commands and all of these commands really are always available on the R pages in Canvas, which are accessed through go to your Canvas site for your individual professor. You can go to Pages and go to View All Pages, and you can find individual pages for R help in regards to your class. So just to make sure everybody's on the same page about some general things in R, if I refer to something as a function, all these things like write.csv, or this thing that says read.csv, or this function called lm, they're all called functions. They take in some input and they spit back out just some output. And obviously, depending on the function, it may take different kinds of input, spit back different kinds of output. Other than that, if you want to read data, there are really three fairly easy ways to input data into R. The first is to do a read.csv and then include a URL that has the data that you want. And if you run this, R will actually go to that URL and find that data for you and drop it over here in what's called your global environment, so you can keep up with it later. You can also manually pull a file from your personal computer by typing in a path and running a similar read.csv function. If you don't know your path off the top of your head, you can always go here to import dataset and go to import dataset and then click from local file. And depending on the version of RStudio you have, yours may look slightly different than mine does, but you can browse around and then pick a file to import, and then you'll get a nice little helping interface that'll help you import the data. Okay, so that should help just a little bit. And you can tell it has a heading, you can tell it has row names, etc., etc., and it'll bring up some data for you. Similarly, you can write CSVs by doing a write.csv function. Also, in general, if you ever have any problems with a certain function, always just type question and then the name of that function. Okay? And then if you hit enter and run that, R will bring up a nice little guide for what that function does. And sometimes it's a little complicated, but it's at least a place to start. Other things that are sometimes useful, for example, I imported this stock market returns data just a second ago, and if I wanted to view it, I could type view and stock market returns, and it has column names. If you ever want to change anything like that or change row names, you can do it with a function like column name, like col names, and I'm taking column names, which I'm generally going to call these things objects, and so I'm reassigning it with this little arrow operator and reassigning it to be a bunch of letters instead of the current column names, which are the actual names of the stocks. C stands for concatenate, so you're just putting a bunch of little strings or names together into one thing. Okay. So if I were to run this, and then I were to review the stock market returns, now all the column names have changed. Okay. Additionally, if you ever want to edit your data, the easiest way to do it is with that little notation, which is just stock market returns, and then I'm reassigning it to be stock market returns, and I have a little square bracket there. If you put nothing, so it's always rows and then columns. So for example, if you don't put anything for rows, it will just automatically keep all the rows from the original data. If you put a minus sign in front of something, it'll say everything except that one. Okay? And if you were to just leave it without a minus sign, it would keep just that row. So I'll show you what I mean. So by running this, I actually just deleted the 5th column from the original data, which was the one marked with the letter E. Okay? So if you ever need to edit data, it's fairly easy to do in R by just doing that little notation. Okay. Now, that's surprisingly useful because, especially in real life, if you ever want to do data manipulation or really work with stats, your data is probably not nice, right? Especially if you're doing homework too, you may run into the fact where you have a row of things that are labeled NA. You can always check for if your data has NA listed in it by typing is.na and then the name of your data frame. And it turns out for me, I don't have any. But sometimes when you import data, if it has any NAs, they'll stick around. They'll prove problematic when you try to run some of these functions on them, like LM or correlation. It might cause the function to error. Okay? All right. Anybody have any questions about R in general before I go on? Sure.
So when putting the NA function, how does one know whether there's an error or not?
Oh, so if you run the the question is that how do you know if there are NAs? So you notice when I ran this is.na function, it gave me this huge, ugly looking thing with a bunch of falses. If there was something that, if you did have a row or a not available, NA usually stands for not available in your data set, you would see true listed somewhere in there. Okay? And there's some more, and if you're, if you have a very large data set, you don't want to scroll through a whole list of true, false, looking for a true. There's some ways you can parse the data and find trues. But I'm not gonna get involved with that right now. Any other general questions about R? Before I go on, sure.
Because when I was using the view function, it shows me an error. It says that I cannot find the function view.
R is okay. So if you have a really common error when when it says cannot find the function, and especially with view, R is case sensitive, which is not necessarily true for all programming languages, but view is capitalized, not lowercase. And if you run it with a lowercase, it will error. Okay. Okay. Anything else before I go on? All right. Okay, so we're going to talk about some actual statistics and kind of use R to show some points and show some things that will come up as you're doing all this analysis. So to do this, we're just going to use the Boston data set, which is the one from the lecture, but I'll be doing a couple of different things with it than what you did in lecture. So I can always just read this CSV, and I happen to know my path where the file is. But again, you can always just use this import dataset button if you don't know what your paths are, or if you don't even know what a path is. So that'll make it a little bit easier. So I could just do this, or I could manually go through import dataset from local file, and then find it. Well, that was the wrong file, and then find it here in my file listing, and it gives me a nice little thing that I can then tell it if I have row names or if I have a heading, etc., etc. And if yours looks slightly different, it's probably because you have a different version of RStudio, but it works pretty much the same. Okay. One other thing about just generalities with R, I really like running this attach function. It pretty much, well, sometimes it throws really long warning messages at you, especially if you've got lots of things imported, but that's okay most of the time. So by running this attach function, I'm going to get those off there. By running this attach function, you don't have to type over and over again the name of the data set. So by doing that, I can type a part of the Boston data set. Let me bring this up. So Boston has a whole bunch of different things about homes in Boston, and MEDV stands for is pretty much the value of the home. And so instead of having to constantly type this, which says go to the data frame Boston and pick out the column named MEDV, instead of doing that, I can actually just type MEDV. It's just a little thing. It's not a big deal, but you may see it throughout, especially when you're looking at homework solutions. Okay. So, all right. So now we'll actually talk about statistics. I know I kind of droned on for a second more about R. Okay, so whenever we're doing stats, we always want, so the vast majority of the time when we're doing the statistical analysis, we're going to be running regressions on various data sets. So, and this is a very common thing to do in reality, right? Like you might want to know, how does some arbitrary variable, maybe sales, depend on a whole bunch of other factors, like maybe how much you're spending on advertising, or maybe how sales are changing over time, or something like that. Okay, and in this case, we'll be looking at Boston home sales as a function of some various statistics that are provided in the data. And in this case, I'm going to be looking at crime rate, the number of rooms in the home, the age of the house, the distance the house is from major work centers, the property tax in the area of the house, a parent-teacher ratio, which is probably just a proxy for how good the schools are in the area of that house, and then something called LSTAT, which is trying to get an understanding of essentially how nice of a neighborhood it is. Okay, so again, whenever I do this, I'm always going to run this little function titled LM, that stands for linear model, and it just literally just does the regression immediately for you. You don't want to have to do a regression by hand. It's very, very time consuming, but we can do it very quickly with a computer. So I'm just going to give it a name here. And it pops up over here in values. And if you want, you can expand this, and you get a whole bunch of stuff that's pretty unreadable. So you generally never really want to do that, but you can always run the summary function. And it gives you something that's much more readable. So summary just summarizes the model. Okay? Does anybody really remember regression from previous stats classes? Okay, so let's go through this a little bit. Would that help? Right? Okay, let's go through this a little bit. So we have, in this summary window, we have a whole bunch of those different variables, right? And you can call them explanatory variables, you can call them independent variables, etc. There's several names for them, but overall they're just variables we're using to predict, in this case, home prices, which is sometimes called the response variable or the dependent variable. Okay. So really what's important here is, for now at least, is this estimate, which is the coefficient. So essentially, this tells you, if you held all these other variables constant and changed age by and increased age by 1 year, then the value of the home would go down by that much. Okay, and if you if you added one more room to the house, then the value of the home would go up by that much. All right. Does anyone think there's a lot of interpretation about the intercept here? What would the intercept mean in this case? Sure.
If there's any change, or if there's no change to the price.
Well, so remember, whenever we do this, so you can think about the intercept literally as kind of like a y-intercept from when we had a nice, just simple regression case. And now you know this thing's in many dimensions and all this stuff, and we don't really need to worry about that. You can really just think about it as it's still kind of almost just like the y-intercept. So in this case, this is the price of the home when all these things are 0. Does that make sense? So many times in regression, your intercept may not mean a whole lot. Okay, it may not make a lot of sense. Okay. All right. Other things that are important when you're looking at this regression summary, hopefully my mic is still picking me up. These things over here on the side, these t-values, and then these things labeled probability greater than absolute value of t. These are your p-values that you might remember from Stats 309, right? And they tell you whether or not a variable is statistically significant. Okay. So, for example, is age statistically significant in this exam? In this, let's say we'll use a alpha of 0.05. Okay. Yeah. So I got a couple of head shakes. No. So it's always good to remember that if your p-value is greater than whatever your alpha is, and by default it's pretty much always 0.05, then this variable would not be statistically significant. And what that means is that pretty much, we don't have enough data, or we don't have, or it doesn't seem like that variable is making enough of a difference, et cetera, to really be able to confidently say that it matters statistically. Okay. A p-value can be thought of as the chance you get the result. The chance you get the result that you did, assuming that the null hypothesis is true. That's a bunch of words, and if you want a better explanation, please see me after. I'll give you a more easily understood explanation. But what else is important here is that pretty much all the other variables are significant, right? Okay. So would you want to include something that isn't statistically significant in your model? Anybody? Sure. You don't have to raise your hand. You can just talk.
What's the downside of keeping it statistically significant?
So if you keep things that are not statistically significant, it can cause some issues. One is that you're kind of incorporating an effect that maybe you really shouldn't incorporate. There's some much deeper issues that we'll kind of talk about later on, however. Keeping these non-statistically significant variables around can cause some problems with your understanding of the other variables. So we generally want to take those things out. And that's easy to do, right? So we could just run some more models. We could just kind of do this almost trial and error approach to statistics and take two different models. One that has all the significant variables in it and one that has all the insignificant in it. This variable is really, really close to 0.05. Since it's not quite under 0.05, I just left it as not statistically significant. Okay. All right. So I'm going to run a couple more models, and all these models is just it's just throwing some data into this linear model function, and it calculates all these things for you. Okay. So before we go on, I just want to show you one thing with what happens when you build a model of just insignificant variables. You probably noticed some weird things happened, right? So those variables were insignificant or not statistically significant in the previous model, but here they are statistically significant, right? So that's kind of surprising, but that can happen. Okay. In a way, if you don't look at the correct variables, sometimes you can misattribute an effect to something that's really not correlated with that effect as strongly as it might seem. Okay, so now that we're looking at this, let's just look at two more things about this regression. Down here you have multiple R squared, you have this thing called adjusted R squared, and you have this F statistic and P value for that F statistic. Okay. So the F statistic is pretty much just a statistic that tells you whether or not your regression as a whole is useful. Okay? So if your F statistic, if the p-value on your F statistic is like 0.2, well, that's a really bad thing. because it's kind of saying your regression as a whole is not statistically significant, which pretty much means your regression's really not worth much. Okay. Lastly, to kind of give you a quick idea, multiple R squared is how much of the variation in Y is explained by all your X's, and then adjusted R squared is kind of a neat statistic. So one of the quirky parts about regression is if you just add more X variables, your R squared is going to go up, right? And you can try it out if you want, but if you add in a bunch of non-statistically significant variables, your R squared is going to go up. And multiple R squared is pretty much just something that penalizes you for having a lot of variables in your model. Okay? Adjusted R squared is what penalizes you for having a lot of variables in your model. And we usually prefer to use adjusted R squared as a tool for model selection as opposed to multiple R squared. We'll talk about that some more later on in the class, I believe, and kind of drive that point home with some more examples. Okay. Does anyone have any questions about what a regression output looks like in R, or questions about parts of it? Sure.
So the multiple R squared is basically the limit. Like for the adjusted R squared, it basically just like take out any non-statistically significant items.
So the multiple R squared will always be greater than or equal to adjusted R squared. There is a formula for adjusted R squared. We don't really show a lot of formulas in this class, but there is a formal formula that literally just takes the multiple R squared and penalizes it by a certain amount based on the number of parameters in the model, and I think the standard error of the model. Did that answer your question? Was that what you kind of meant?
Because you mentioned that the adjusted R squared involves some of the non-statistically significant items, so multiple R squared just penalizes it for using those variables.
Oh, adjusted R squared will penalize it for having whether or not the variable's statistically significant. You can think about it like, well, if you added a variable and it was statistically significant, but it didn't increase your R squared by very much, maybe it's not worth it to keep it in the model, right? Maybe in real life you'd have to go get data on that, you'd have to spend money to get data on that. And if it's not doing a lot to your model, then maybe you don't want it. And from a statistical standpoint, it's a very similar thing. Maybe that variable does add a little bit of R squared to the model, but it's not enough to justify complicating your model further. We prefer simple models over more complex models, unless the more complex model has a clear benefit, such as a much, much higher R squared. And better things in general, like better assumption, better adherence to the assumptions of regression. Okay. I'm going to go on and talk about assumptions for a minute, so I can kind of get through what I want to talk about, and then I can take individual questions. Okay. So there's several assumptions in regression, but the important ones for this class for right now are independence, linearity, constant variance, and then the normality of the residuals. So those are the four things you need to check. Independence pretty much means that the error for the first data point is independent from the error for the second data point. And in practice, especially when you have data over time, that assumption can be violated, and it's a pretty problematic thing to have violated. For now, it's very hard to check graphically. Unless you have a good reason as to why it would be violated, you can generally assume that it's not going to be violated for now. Okay. The next thing to check is linearity. So, this whole idea of linear regression is we're drawing a straight line through a bunch of data, right? Well, if your y variable and your x variable don't have a linear relationship, then maybe that doesn't really work so well. So that's a good thing to check. And in single regression, it was pretty easy to check that because we just drew some scatter plots and we were pretty much done. In multiple regression, it gets a little bit harder. You can kind of do a similar thing. You could say individually plot. So I'm just running a plot command, and then it's crime. So it's one of the x variables versus the y variables. And you can look at this. You can look at this and try to figure out whether or not there's a linear relationship. Let me see. And overall, it looks a bit weird, especially because this is crime rating. So the crime rating is unsurprisingly very, very low as soon as home values go up above a certain point, right? But once you kind of get away from that, it looks pretty linear, right? So one of the things about assumption checking is it is somewhat of an art. So kind of do the best you can and don't overthink something. If it looks pretty linear, it probably is, okay? However, it's very important to also not only check these individual scatter plots, but to also check a plot of the residuals. So this is a plot of the residuals versus all the fitted values of the model. Okay? Now, if there's a pretty noticeable pattern in these residuals, then that is a problem, right? So that would say something like, you know, when your y values were small, maybe your model's doing a better job of fitting than when your y values are bigger. And that can mean a whole number of things, but one of the things it can imply is that there's not a linear relationship between your y and your x variables. So this is also a good thing to look for, and we'll come back and look at this again in just a moment. But if there's a pretty pronounced pattern, like, you know, if the residuals go up and then back down or something like that, then that's an issue. You can also do things that are a little more complicated. And if you look on your PowerPoints for Lecture 8, they use this thing called a CR. Well, in R, it's called with CR plots. It's actually part of this library called CAR, which is just a library to do some more advanced things in regression. And you can load the library. And if you ever need to install anything in R, you can just go to Packages and click Install, type the name of the one you want, make sure that you install all the dependencies, and then click Install. Okay. So you can do something that's a little more advanced, like these. Zoom in on this. So these are nice. They're a little bit more advanced of a way to check for linearity. Essentially, we're trying to check to see if the effect of one of these variables, such as crime, is linear with the rest of the model. So, you know, once you've accounted for the effects of the other variables, is there still a linear relationship? And really what you're looking for is for these lines to match up pretty well. So this red line is a straight line through it, and this green line is the kind of a fitted line for the data you see. So for example, the one for room looks a little bit off, right? So this might imply that there's not a linear relationship. Okay. All right. So I'm going to go ahead on. Later on in the class, we'll talk about how you fix these problems. So, you know, if your relationship isn't linear, then your regression may not work very well. There's ways to fix that. We'll talk about it later. Kind of the next major problem to check for is this thing called heteroscedasticity, which is a really big word for the variances not being constant. You can check that in two ways. One is to go back to that thing we just looked at, which is a plot of the residuals against the fitted values. And what you're looking for here is a fan shape. And what I mean by that is here's an example of something that has heteroscedasticity. You see how there's a nice fan shape in these residuals? That's a bad thing, because your variance on the left side is small, your variance on the right side is big, and we need that to be constant for our regression to work properly. Okay. So in this case, it doesn't look too bad. Again, you can do something a little more complicated called a spread level plot. And again, in this case, you kind of want the green and the red arrows and the red lines to match up a little bit. And in this example, it's not working super well, and it might be because there's some outliers in the data or something like that. So this plot will also spit back this thing called a power transformation. Again, more on that later in the course. Okay. But yeah, so you want these lines to kind of match up if you're checking it with this plot. It is significantly easier to check it with the previous one and just look for those fan shapes, but it may not. That method may not work quite as well as this one. Okay. All right. Other things you can do, you can check for the normality of the residuals. So you can make a histogram, and if you make a histogram, you're looking for a nice bell shape, right? And that looks more or less okay. There's some outliers, maybe not great. Another thing you can do is run these two functions called QQ-norm. And on a QQ plot, you just want you want all these things to line up on a nice 45-degree angle. This pretty much checks to see how much your residuals actually look normal. So it just checks to see how much your residuals actually look normal. QQ plot is another slightly more advanced thing you can do that sort of draws some lines on there kind of as a reference point. And so here you can kind of see that those outliers, you can kind of see those outliers from the histogram. You can see them here too, up here in the corner. Some weird things are happening. So maybe this isn't quite normal.
So do you need both?
You usually want to check both a histogram and a QQ plot just to make sure. A QQ plot is a little more formal. There's a lot of ways to check for normality. There's more algebraic ways to check for it as well. But we don't really cover that in this course as far as I know. Okay. All right. So that was assumption checking. So this is just a bunch of R commands to kind of look at these things. And again, if these assumptions are violated, so if your relationship isn't linear, if your errors aren't independent, if your variance isn't constant, if your residuals aren't normally distributed, also if you have outliers in the data, your regression may not really be that reliable. Your results are something that can't really be trusted, which is why we constantly check these assumptions every time we do a regression. Okay? All right. So we saw these, and there were several instances where these didn't look all that great, but for now, since we haven't discussed how to fix these problems, we're just going to kind of accept the model as is and continue working with it. All right. Any questions before I kind of keep going? Sure.
You mentioned outliers. Which assumption is it associated with linearity?
We'll talk about outliers in more detail later. There's some people think of them as like I was taught that they're like their own assumption, where your data doesn't have outliers. There is something that is very important to check for. They can, especially depending on like one outlier can cause a lot of problems to your entire regression in some cases if it is sufficiently outlying, I guess. I don't know how to say that, but we'll talk about formal ways to look for that later. In single variable regression, it was very easy to see outliers. You just made a scatter plot, and if a point was like way away from all the other ones, well, that was an outlier. But now we're in multiple regression, and you have 5 or 6 variables, and you can't graph 5 or 6 variables all at the same time. So we need a more analytical way to check for that, and we'll get to that later on. All right. Okay, so the last couple of things just to kind of show you some more things that R can do for you. So it's important to note, when I was up here and I made this model with just the significant variables, I named it model signif. And you notice that a lot of the time I was just, calling this function on the model itself. It's good to keep track of these models in general. So something we can do is we can kind of we can take a regression, and the whole point of a regression a lot of the time is to get nice predictions out of it. So we might want to predict the value of a home if we knew that the home had these statistics about it. You know, it was 88 years old and the tax bracket it was in was 244, etc. And I just randomly picked these values. And they're sort of in the middle of the data we have. Just to go ahead and note on that, just go ahead and note this. If you're trying to predict something that is very different from the data you used to build your regression, that might be a bad idea. Your regression may do a very poor job of actually predicting that value. So the further away thing you're trying to predict is from the data you have, the more kind of like you're kind of like extrapolating from the data, and your result may not be all that accurate. Again, we'll talk about that more when we talk about outliers. So here I'm just making a new data frame. I'm just calling it new stuff. And data.frame makes a data frame with all these different columns and headings. So if I run this, I made this, and if I view new stuff, I have a nice little data frame here. Okay. There's different ways you can run this function, but I like doing it this way. And I'll show you why in a second. So if I wanted to predict the price of a house with those statistics, I can just use the predict function in R. I can run that, and it predicts me a median value of 545, and that's in thousands. Okay, nice, straightforward, and easy. So that's the best guess you have at the value of the home. There's different ways you can do this. You don't have to make the data frame. You can just tell it new data equals data frame, etc. But there is a good reason to do it this way, where you make a data frame. So if I take that new stuff data frame and use rbind, that stands for row bind, I can just rbind new stuff with maybe another house that I want to make a prediction about as well. And so I'm just concatenating all these values together. And so right now, new stuff looks like that. And if I run this function, now I have another house. I have another data point to predict. Okay. All right. So if I want to make a prediction about just the second one, then I can tell it that to take new stuff. And if you remember back at the very beginning, I talked about brackets and bracket notation. If you do a square bracket and then a 2 and then comma and then leave the next part blank, it says just the second row, and then since you left the column section blank, it takes all of the columns. So I can predict a value for the second house, and it's 743, or I could just predict both houses at the same time, and then it would spit out the prediction for the first house and the second house. Okay, is that all right? Okay. Lastly, just to kind of tie things up, and I'm going to talk about these more. I'll kind of draw some confidence intervals and stuff and make sure everybody's on the same page with them. If you need a confidence interval on your prediction, so you can never just give a best guess, right? Because the thing is you're probably not going to be exactly right. Okay? You had some data. You're not going to be perfect. So what you do is you give them a confidence interval that gives a band that the true value should most likely fall into. Okay? So you can do that by just running the conf int function. You tell it what model you want to look at. You give it some confidence level. I just picked 92. You can do 95 if you want, or anything. If you run that, it gives you the confidence intervals on it gives you the confidence intervals on every single predictor. So before, when we ran the summary of the model, it gave us a whole bunch of coefficients on each variable that were kind of like the slopes. So if we held all the other variables constant and changed the crime rating, then the value of the home changed. Well, this is a confidence interval on all of those values. Okay. I'm just going to jump down here since I was talking about this a second ago. If you wanted to give a confidence interval on your prediction, then you can run predict.lm. It's essentially a very similar thing to predict. And if you run it, and again, I'm running it with the first data point that I made up. So it gives you a confidence interval, so it gives you the best guess under fit, and then the lower bound of the confidence interval is there, and the upper bound of the confidence interval is there. And you notice that I'm telling it interval confidence and interval prediction. So if I run the prediction, well, the prediction interval is wider, right? Okay. So does anybody remember the difference from 309? Or any stats course you may have taken? Sure. Yeah, the difference between the confidence interval and the prediction interval. Yeah, somewhat. Yeah, so you can think about the confidence interval as you're trying to predict the average house with those data values, and the prediction interval is trying to predict a particular house with those data values. It's much easier to predict the average than it is to predict a particular entry. For example, it's much easier to predict the average height of a person who comes in through the door as opposed to predicting the height of the next person to walk through the door. Okay. All right. Last little thing. If you ever need to pull your residuals for any reason, you can get them manually if you want to for some reason. So you could do that by just picking up the home value. So this is just to get the 10th data points residual. You can run predict. So you can take the 10th value from Boston. I just gave it a name called temp house. So if I run this, and then I run this, just to show you what temp looks like. So temp is the predicted value for that house. And then if I want the difference between the actual value of the house and the predicted value of the house, I can do it manually like this and find out that in this case the model is predicting slightly higher than the actual home value. Okay. All right. And if you don't want to do it manually, you can do it like this, where you ask the model, you call the model, and then you call its residuals using the $ command, and then you tell it you want the 10th residual. Okay? You only need one. You don't need a comma here because the residuals are just one vector. So there's only one number you need to pick out the particular residual you want. Okay. Okay. All right, so that was a lot. And I know I haven't had a lot of time to cover stats itself. Hopefully the R tutorial was helpful. I'm going to end the video there and then take some questions, and then I'll probably stay for a bit and take questions. So hopefully this was helpful. And yeah.